class we can discussing about the electrical measurement subject. Okay, so in this one you have to discuss in the third unit measurement of power and energy. In this class we can discussing about the power factor meters. Okay, what is power factor meter? What is the need of the power factor meter? And then what are the types and working of those power factor meters? Those are all discussed in this class. Okay. Power factor meters. Okay, so we know that power factor. Okay, power factor is, so actually the power value will be the power measured across any parameter is nothing but P equal to VI cos phi. So in this one, cos phi is nothing but power factor. So whenever you want power factor, so at that time you can write cos phi equal to P by VI. So here P means wattmeter reading, V means voltmeter reading, and I means ammeter reading. So that means here you have to find out the cos phi power factor value. We need at a time 3 meters: voltmeter, ammeter, wattmeter. So by using these 3 individual meter, so by using voltmeter we have to find out the voltage value, and by using the ammeter we have to find out current value, and by using the wattmeter we have to find out the power value. So at that time these all values are substituted in this formula. At that time only you can get the power factor. So that means you have to need at 3 meters. So to avoid that one, so these all are, so the power factor value is measured at a single meter. So that is nothing but power factor meter. Okay, so you have to introduce the another one meter to find out the power factor value, that is nothing but the power factor meters. Okay, see, power factor meters are 2 types. What are those? Electrodynamometer type power factor meter, moving iron type power factor meter. Okay, so what are the types of power factor meters? Electrodynamometer type power factor meter and moving iron type power factor meter. And again, these moving iron type power factor meters are classified into 2 types. Those are rotating field type power factor meter and alternating field type power factor meter. Okay, so coming to first, let us discussing the electrodynamometer type power factor meter. Okay, so this is the construction of the electrodynamometer type power factor meter, and this having the 2 coils, pressure coil and current coil. Okay, so and here you have to using the 2 magnets. Okay, A and B. So on this one here you have to connect a pointer, and this one is a scale. So power factor means power factor you have to measure the unity power factor, okay, lagging power factor and leading power factor. Okay, so this will be represents the lagging power factor value, and this will represent the leading power factor value, and this one will be unity power factor value. Okay, so whenever so see, this is the supply side and this is the load side. Whenever we have to giving the supply, okay, so at this time these magnets experience a force, so at that time the magnets will move, so like this in this direction. Okay, so at that time, so here you have to exist a field coil, you have to using the 2 coils, field coils, that is pressure coil and current coil. So at that time these exhibits some magnetic field, so at the time, so this will be moves like this. Okay, so this is the rotation of the pointer. Okay, so this is the construction of a electrodynamometer type power factor. See, the torque exhibits at A is nothing but TA equal to KVA cos phi cos 90 minus theta. See here, A will be moves at the angle of 90 minus theta. So similarly, the torque exhibits, okay, the torque exhibits and B will be TV equal to KVA sin phi cos theta. Whenever you have to take the equilibrium position, okay, so at equilibrium position, what happened? TA value will be is equal to TB. So that means this value will be is equal to this value. That means kVi cos phi cos 90 minus theta equal to kVi sin phi cos theta. So at the time kVi get cancelled. So cos phi cos 90 minus theta equal to sin phi cos theta. Cos 90 minus theta is nothing but sin theta. Okay. So whenever you have put cos phi this side, so sin phi by cos phi will become tan phi cos theta. And you have to put cos theta this side, sin theta by cos theta will become tan theta. So tan theta is equal to tan phi. So at the time theta is equal to phi. So that means, so what is that meaning? So whenever the pointer will move, that the deflection of the pointer will be how many degrees will be deflected, that deflection will be is equal to the power factor value. Okay, so that is the representation. Okay. Coming to the advantages and disadvantages. So advantages, the dynamometer type power factor meter does not require the controlling torque. Okay, so there is a no need of the controlling torque. So at that time, if you have to provide the controlling torque, so at that time you have to provide the gravity control, okay, spring control like this. So but here there is a no need of the dynamometer type power factor meter does not require the controlling torque, and its construction is robust. Okay, so construction is also robust and it requires the little maintenance value. So coming to the disadvantages, if the supply consisting of the harmonics, it gives rise to serious errors in the indication of power factor meter. Okay, if suppose at the starting the supply consisting of the harmonics, so at that time it causes the serious errors in the indication of the power factor. Okay, so these are the disadvantages. So what is the second type of the power factor meter? Moving iron type power factor meter. Okay, so this is the construction of a moving iron power factor meter. Okay, this is consisting of the three field coils F1, F2, F3, and here you have to place a one coil. Okay, so this is the three-phase supply, and okay, this is a three-phase lead. Okay, these are field coils are connected to the supply through a current transformer. So the first one is rotating field type. So see here like this. Here you have to coil placed. Okay. So see whenever you have to place the coil in this field. So at that whenever you have to giving the supply, these field coils will exhibit the flex. So because of this flex, this coil will be moved. Okay. Coil will be exhibiting some force. So due to that force, the pointer will shows the deflection like this. Here you have to place the coil. Okay, so whenever in the coil there will be exhibits the force, so at that time it moves that force will move the damping vane. So at that time the damping vane will deflects the pointer and the pointer will shows the reading value. Okay, see here rotating field type power factor meter working. Okay, see here there is no controlling torque acting on the system. Here also there will be no need of the controlling torque. Okay, the voltage coil. Okay, the voltage coil, that means central coil connected across any two phases produces an alternating flex. Okay, so the coil, central coil will have to you have to connect it across any two phases. See here, coming to this diagram here. Here the coil will be placed. This coil will be connected to any two phases. That is RY phase or YB phase or BR phase. Okay, or YB, any two phases or three phases. So at that time it exhibits the alternating flex. Okay, since we have to connect the central coils across the two phases of the system, the current through it is in phase with the system voltage. So at that time, whenever you have to connect it to that central coil to any two phases, okay, any two phases, at that time the current through it. Okay, so at that time the current through that coil is in phase with the system voltage. Okay. Similarly, the angular position of the pointer, that is moving iron system, depends on the phase difference between the current of the central coil and current coils. Okay. The surrounding you have to place the three current coils. Okay, F1, F2 and F3. So here the pointer angular position, the pointer will shows the deflection. The deflection of that pointer, that angular position will be depending upon the phase differences between the current of the central coil, okay, and current coils. Okay. Here hence the deflection of the pointer equals the angle of a phase difference between the current and voltage in the three-phase system. That means how much deflection it shows, that deflection will be equal to the power factor. Okay, so that is the rotating field type power factor. The next one is what? Alternating. So in moving iron type power factor meters, we have two power factor meters again, that is alternating field, okay, rotating field. So previously we have discussing about the rotating. So next one is what? Alternating. Here you have to take the three iron pieces, P1, P2 and P3. Okay, and this one you have, you have to take C. Okay, you have to take this is the supply side and this is the load side. Okay, so and here you have to, on the spindle you have to connect the current coil through three iron pieces. Okay, these are the three iron pieces, and here the pointer you have to connect the spindle. Here this is a damping vane. Okay, just this is the symbolic representation of the alternating field type power factor meter. Okay, this is the supply. Okay, main. Okay, line means load. Okay, these are the three voltages. Okay, see, coming to the working of the alternating field type power factor meter. See, when current flows through the current coil, whenever the current will flows through the current coil and the voltage coils, the moving system starts rotating and rest on the position that the main torque upon iron pieces is equal to the, see, here you have to connect, I will say, the three iron pieces. So whenever the current will flows through the current coil, okay, whenever the current will flows through the current coil and voltage coils, the moving system, okay, so at the time the moving system will starts rotating and rest on a position that the main torque. So whenever the torque exhibits on the one iron piece is equal to the opposite to the resultant torques of the other two iron pieces. Okay, so therefore the net torque acting on the moving system becomes zero at the steady state position of the moving system. So at that time the net torque, so that means that exhibits on the one of the iron piece is equal to the resultant of the remaining two. So at that time the net torque acting on the moving system will becomes zero at the steady state of, so that means at the steady state. Okay, there is one iron piece connected to the voltage coil of that phase in which in series with the current coil. So when so when one iron piece connected to the voltage coil of that phase each series with this. So here you have to, so whenever you have to connect the iron piece to the voltage coil and current coil, at that time that iron piece will be deflected. Okay, at that time the deflection of that iron piece is equal to the phase angle between the voltages and currents of the three-phase supply system. So here you have to giving the three-phase supply system R by B. So at that time whenever the iron piece deflected, so at that time the deflection is equal to the phase angle between the voltage and current of the three-phase supply system. Okay, that deflection is equal to the power factor value. Okay, so coming to the advantages and disadvantages. Okay, so advantages. The scale of the instrument can be extended up to 360 degrees centigrade. Sorry, 360 degrees. Okay, so that means the scale. Okay, the power factor meter scale will be extended up to 360 degrees. Construction of this instrument is robust and simple. Okay, construction is also robust and simple. They are cheap. Okay, the deflecting torque of this instrument is more than that of a dynamometer type power factor meter. So here in this one the deflection torque is, so in alternating field type power factor meter, the deflection torque of the instrument is more than the dynamometer type power factor meter. Disadvantages. Okay, coming to the disadvantages, the loss occurs in the iron part of the meter. Okay, here only the loss occurs in iron pieces. Hence the meter has low accuracy. Whenever the losses will be occurs, so at that time the efficiency of the meter will be decreases. So that's why it indicates the low accuracy. Okay, the calibration of the meter is affected because of the variations in the supply frequency, voltage and waveform segregation. Okay, so the meter calibration affected. Why? Because where there will be any variations in the supply frequencies, voltage. Okay, so these are the advantages and disadvantages of the alternating field type power factor meters. So up to now we have to discussing the how you can measure the power. Okay, what are the power factor meters? So in this unit also you have to discuss the energy meters. Okay, measurement of energy. How you can measure the energy? Okay, so that is by using the energy meters. So here here also you have to see the construction of the energy meters, working, all those are. So energy meters. See, the meter which is used for the measuring the energy utilized by the electrical loads is known as the energy meter. The meter. Okay, so the meter which is used for the measurement of energy utilized by the electrical loads. So whenever the electrical loads will uses the energy, so that energy will be calibrated by using the one meter. That meter is nothing but the energy meter. The energy. So what is the energy? The energy is the total power consumed and utilized by the load at a particular time interval of time. So energy is nothing but the total power consumed and utilized by the load. So any load, the total power consumed or utilized at a certain particular time period. Okay, that means particular interval of time. That is nothing but the energy. Okay. See, here energy can be expressed as integral of 0 to t. So here you have to say that particular interval of time. Okay, so that's why here you can represent E equal to integral 0 to t power of dt. Power is nothing but Vi. Okay, so at that time you can write 0 to t Vi dt. Okay, so see, to find energy, so here to find the energy we have to use the energy meters. See, the energy meters are classified into two types. Okay, mainly the energy meter according to the supply. Those are single phase energy meter, three phase energy meter. Okay, so the energy meters are classified into how many types? Two types. What are those? Single phase energy meter, three phase energy meter. So single phase energy meter. See, single phase energy meter. Okay, so that is also nothing but you can say that single phase induction type energy meter. Okay, that means for single phase you have to find out the energy value. We are using the single phase induction type energy meter. Okay, there are mainly four parts in operating mechanism in energy meter. In this one, in single phase induction type energy meter, there are mainly four parts. What are those? Driving system, moving system, braking system, registering system. See, so energy meter. So in our household purpose, we are using the energy meter is nothing but the energy meter. So this is in household purpose, we are using the energy meter. That is nothing but the single phase induction type energy meter. Okay, so this is the construction of the single phase induction type energy meter. Okay, see, so it is uses the two magnets. This is the upper magnet and this having the lower magnet. Okay, so this upper magnet is called as shunt magnet. Okay, so for upper magnet you have to connect the pressure coil, and lower magnet pressure coil of high number of tons. Okay, so the upper magnet is connected to the pressure coil of high tons, and lower magnet is connected to the current coil of the less number of tons. Okay, for the pressure coil you have to connect the more number of tons, and current coil you have to connect the less number of tons. Okay, these two are giving to the supply side and to the load side. Okay, so and on the disc, so this is the spindle. Okay, this is the spindle to recording mechanism. On the spindle you have to connect the disc. Okay, near the disc here you have to connect the one braking magnet. So on the upper magnet here you have to connect the copper shading bands below the pressure coil. Okay, so this is the construction of the single phase induction type energy meter. So this is a bearing supporting system to this spindle. Okay, so coming to the working. Okay, now you can discussing the working of the single phase induction type energy meter. See, it works on induction principle. Okay, so here the single phase induction type energy meter is working on the induction principle, that is on the production of eddy currents in the moving system by the alternating flexes. Okay, induction means whenever current will passes through the one coil, so it produces the flux. That flux will be linked with the another coil. That is nothing but the at that time it produces the flux value. So that is nothing but the induction principle. Okay, so it works on the induction principle, that is on the production of eddy currents. Okay, eddy currents in the moving system by the alternating flexes. These eddy currents induced in the moving system and the magnetic field interact with each other to produce this torque on the moving system, which exerts a force on the disc. Okay, see here the eddy currents. Okay, the currents. So whenever the according to the induction principle, okay, whenever the flux will be linked with the another coil, so at that time it produces the current value. So that is nothing but the eddy currents. The eddy currents induced in that moving system and magnetic field, and that magnetic field will be interact with each other to produce the torque on moving system. So at that time they will be exerted torque. So here, so in previous diagram you have to see the disc. So at that time they will be exerted torque on the disc. So at that time the disc will be rotated. Okay, at that time the disc will start the rotating. So here driving, I will say is the driving system. So main system is driving system. Okay, braking system. See here, whenever you have to giving the supply, so at that time, first the flux, so here the flux will be produced in this magnet. Okay, this flux will be linked with this lower magnet also. Okay, so at the time interaction of this upper magnet and lower magnet, the disc will be rotated. So at that time the spindle will move. So at that time it recording the values. Okay, so here braking magnet. Okay, so braking magnet is used for the proper disc rotation. You have to adjusting the here braking magnet. So copper shading bands means, so whenever the eddy current loss will be occurs more, so at that time it causes maybe damages. So to avoid that one, here you have to use the copper shading bands. Okay, so so in previous we have discussed driving system, braking system, moving system, resisting system. Okay, driving and braking down. So driving means the pointer will deflect. So the operation done up to that pointer will deflect. That is nothing but the driving mechanism. Okay, so at that time it produces a deflection torque. TD is proportional to VI sine delta minus phi. Okay, so see here V. Okay, so this is the V. This is I. Okay. Okay, this is the phasor diagram for the energy meter. So at the time TD equal to, here you have to write the one constant whenever you have to remove the proportionality. So at that time K3 VI cos phi. So TB, braking torque. Braking means whenever it takes will register the, at that time you have to must to stop. To stop that one, you have to using the braking torque. So that braking torque is proportional to N. N is nothing but number of rotations. Okay, so that means how much revolutions will be done by the energy meter. So that is TB equal to K for N. For the steady state operation, TD equal to TBS. That means deflecting torque is equal to the braking torque. So at that time K3 VA cos phi is equal to K4N. Okay, so at that time K3 by K4. So K3 by K4 you have to write, that is a one constant, that is the K3 and K4 both are constants. So at that time you have to write the constant K3 by K4 means K VA cos phi. Okay, here VA cos phi is nothing but power, K power. So at that time the number of revolutions, integral. So number of revolution you want, so this is the total, so this is the revolution. So you have to get the number of revolution per particular time period. So at that time you have to write 0 to 2 N dt. 0 N value means K into power, K power dt. So here K is a constant, power is indicate PDT. So the total number of revolutions is equal to K into energy. So that means how you can measure the energy value is the total number of revolutions by the disk. So here you have to connect the disk in between upper magnet and lower magnet. So how much revolutions it measures, so that value will be taken as the energy. Okay, so that is the working of the energy meter. Okay, coming to the advantages of energy meter. So it has high driving torque. Okay, so the torque of the energy meter is high. The cost is also less. Okay, so the cost is also less. It has more accuracy. Accuracy is also more. Coming to the disadvantages, it consumes high power. Okay, consumes high power. It is only suitable. It is suitable only for AC measurement. Okay, it is suitable for AC measurement. Creeping error creates problem to the consumer. Okay, so in this one, creeping errors will be produced. Okay, to reduce that creeping errors, here you have to using the braking magnet. Okay, so these are the advantages and disadvantages of the energy meter. Creeping error. So here you have it says that, so in energy meter the errors main occur is nothing but creeping error. So what is the creeping error is? The slow but continuous rotation of the energy meter which only pressure coil excited but no current flows to the, see whenever sometimes this continuous rotation of the energy meter, at that time only pressure coil will be excited but no current coil will be flows to the current coil. So that problem, that error will be called as the creeping error. Okay, so in order to prevent creeping on no load, so creeping errors are must and should exist on no load. Okay, two holes are drilled in the disc. So to avoid the creeping error, two holes will be drilling on the disc on the opposite side of the spindle at the same radius. Okay, on the disc we have to drilling the two spindles of the same radius. Okay, this causes sufficient distortion of the field to prevent the continuous rotation. Okay, so at that time it causes to prevent the continuous rotation. Whenever you have to prevent the continuous rotation, so at that time the creeping error will be also reduced. See, the various errors occurs in energy meter and how you can compensate that one. See, the various errors and compensation of single phase energy meter, phase or lag or power factor error. So first error is what? Power factor error. So in some cases, because of the distortions in the power factor, the errors will be occurs. That errors will be reduced by using the copper shading bands. So here you have to shade at the bands. Okay. Next one, speed error. Okay, so sometimes at that time the disc speed will be varies. Okay, because of some errors, those are reduced by the position of the braking magnet. So that means the braking magnet is used to adjust the speed of the disc. So next one is creeping error. Previously you have to, creeping error is very important. Okay, so in some cases what is the creeping? For short answers maybe ask what is creeping. Okay, creeping error. Okay, to reduce the creeping error, you have to put the two holes on the disc. Okay, this is also one error. Next one is what? Temperature error. Okay, so there will be up and downs. Okay, there will be temperature rise. Okay, the errors will be occurs. So whenever temperature will be increases, so at that time it may be causes the eddy current errors. So you have to use the shunt. Okay, you have to put the shunt winding on the braking magnet to avoid that temperature error. You have to shunting on the braking magnet. Next one is what? Overload compensation. So whenever the load will be overload, so at that time it may be causes the, whenever the load will be overload, so at that time it causes the excessive current. Okay, to reduce that one, here also you have to use in the magnetic shunt. Frequency error, maintain frequency constant. Whenever you have to maintain the frequency value will be constant, at that time you can avoid the frequency error. So next one is what? Voltage variations. Okay, there will be some voltage variations will be occurs. To reduce that voltage variations, replace the shunt magnet by the saturated shunt magnet. Okay, to vary the up and downs in voltage variations, you have to replace the shunt magnet by the saturated shunt magnet. You have to take this small problem on the energy. See, at 240 volts, 5 amperes, single phase energy meter has a constant of 1200 revolution per kilowatt hour. Okay, when tested by applying 240 volts, the meter took 99 seconds to complete 40 revolutions. Find the percentage error. It is running fast or slow. Okay, so here you have to take the 240 volts. Okay, 5 amperes single phase energy meter. Okay, so here you have to take the 240 volts. Okay, 5 amperes single phase energy meter has a constant of 1200 revolutions per kilowatt hour. Okay, so when tested by applying 240 volts, the energy meter took how much time period? 90 point to complete the 40 revolutions. Okay, see here the total energy consumed formula is VIT cos pi, and that means PT. Energy means P means power, VI cos pi. V value will be 240 volts, I value will be 5 amperes, T value will be 98.9 seconds by. So here the seconds will be converted into the hours. Okay, so at that time you have to write 98 by 3600 into, here the power factor will not be mentioned. So whenever you have it in any problems, the power factor will be not mentioned. So at that time you have to take the power factor value will be unity 1.0. So at that time the total energy is the indicated reading. Okay, indicated reading is revolutions made per K in revolutions. See, revolutions made 40. Total revolutions are 1200. To convert this one watt hours, so at the time you can multiplying with 1000. So at that time you have to get the 33.33 watt hours. Okay, the indicator reading for value will be 33.33 watt hours. So that means the total, but here you have to find the percentage error. Okay, so at the time C, the energy error, thus energy error is equal to total energy, indicated energy. Total energy value will be 33.267 minus, so this is the energy error. Okay, so percentage error into 100, that means 0. Percentage error means 0.66. Okay, that means the energy error by total energy into 100. Okay, so energy error will be 0.066 divided by 33.2667 into 100%. So at that time here you can get minus 0.2% more. That means since the energy recorded is more, okay, the energy meter is running fast under the given operating condition. So that means here the percentage error will be minus 0.2%. See here, the meter constant of another problem. You have to take in the another problem. The meter constant of an energy meter is 1200 revolutions per kilowatt hour. Okay, so you take 1200 revolutions. It is found to make 20 revolutions in determine the load on the energy meter. The total energy consumed is nothing but revolutions made per kilowatt in revolutions. Okay, revolutions, how many revolutions? 20 revolutions divided by total revolutions are 1200. So at the time the total energy is consumed in it. The load on the meter is energy in kilowatt hours by time in hours. Okay, so 0.016 by 80 by 3600. Okay, so that means to convert in hours. So at the time you have to divide in that 80 by 3600. So at that time here you have to get the 0.75 kilowatts. Okay, so that is the solution. Okay, so next in the first you have discussing the single phase energy meter. So here for measuring the three phase value, here you have, so there is a no need of the construction operation, just in our subject point of view, just you know the three phase energy meter diagram. Okay, so see, three phase energy meter or two element energy meter. Okay, so the three phase energy meter will be called also two element energy meter. Okay, see here the three phase energy meter. Okay, the three phase energy meter having two elements. See here R, Y, B. Okay, that means two elements. That means one element having upper magnet, lower magnet, and another element having upper magnet and lower magnet. These two elements will be given to the three phase supply. Okay, so that means it measures the three phase energy. Okay, that's why this is called the three phase energy meter or two element energy meter. So here you have to take in the shunt magnet. Okay, so that means this is one element shunt magnet, this lower magnet, this is the upper magnet. Okay, these two will be connected through a spindle and bearing system pointers. Okay, so this is the supply side and this will be a load side. Okay, so see these two are giving these two. So whenever flux produced in the one element will be linked with the another element. So at that time that finally the two discs will be rotated. Okay, at that time the total resultant value will be taken as the sum of these two values measured by the two elements. Okay, so this is the general symbolic representation of three phase energy meter, three phase load. Okay, RYB three phase supply, first element pressure coil, current coil, second element pressure coil, current coil. Okay, that means these two are connected in a series. Okay, so that's why this is called the three phase energy meter. That means the torque of the both elements is added mechanically and the total rotation of the shaft is proportional to the three phase energy consumption. So that means here that three torques. Okay, so that means two elements. Okay, two elements exhibits the two torques. Whenever you want the resultant torque, the two torques will be added. So that means the rotation of the total torque will be equal to the proportional to the three phase energy consumption. Okay, that means whenever the torque will be added, the total energy consumed by the two elements will be added. So at that time you can get the total three phase energy consumption. That is the two element energy meter. This is the three element energy meter. That means here three elements connected in a series. This is one element, this is another element, and this is third element. So first element having P1, C1, pressure coil, current coil. Second element having P2, C2, say pressure coil, current coil, and third one is also P2, C2, P3, C3. Okay, these all are connected in series. Okay, these having shunt magnets, series magnets. That means upper magnets and lower magnets. So these all are connected in series. So this having three phase load, and here also you have to connect the neutral R by BN. Okay, and it is given to the load. So whenever we have to giving the supply, these 3 element disk will be rotated and 3 will be produced as the torque. At that time you have to get the resultant torque is the sum of the 3 individual tasks produced by 3 elements. Okay, see this is the symbolic representation of the 3 element energy meter. Okay, so see here also current coil, pressure coil, current coil, pressure coil, current coil, pressure coil. These all are connected in series and it is giving to the 3-phase load. Okay, the load and supply. Okay, so this is the 3-phase element energy meter. Okay, so up to now in this unit we have to discussing about the measurement of the power and energy. How you can measure the power value and how you can measure the energy value. So, but that is in both in cases of single phase and 3 phase. Okay, thank you.